Hi, my name is Tate Schneider, and today I will be making invisible ink and explaining how indicators work. The first thing you need is phenolphthalein. You need 10 milliliters of phenolphthalein to make 100 milliliters of invisible ink. In order to get the phenolphthalein, you should use a graduated cylinder and a funnel. Then just add it to the beaker that you want to keep your invisible ink in. The next thing you need is 90 milliliters of distilled water. I only had 40 milliliter beakers, so I had to use 2 of those and one 10 milliliter portion of distilled water. After measuring out your 90 milliliters of distilled water and you have added them all to the beaker that you want your invisible ink to be in, you will swirl it around, and the next thing you want to do is add 20 drops of a base. In this experiment, I chose to use sodium hydroxide as my base, and I will be using acetic acid as my acid. After you have added the 20 drops of base, then you should swirl it around until it becomes not cloudy anymore. It's like ink. Notice that when it hits the paper, it is invisible because the paper or the atmosphere is slightly acidic, or it could be because I added water. Now, using a cotton ball that has been dabbed in the sodium hydroxide solution, wipe across the writing that you put on the paper and it will reappear, just like how the acid made it disappear. After using another cotton ball dabbed in acetic acid again, if I re-wipe the solution that I just wrote on, it starts to disappear again. Invisible ink is a chemical reaction between the sodium hydroxide and the acetic acid in the vinegar, which produces water, and it produces the ions of the sodium positive ion and the CH3COO- ion. This is an example of an acid-base reaction which reduces a salt with the sodium and the CH3COO- ions and water. The indicator of phenolphthalein that we use serves as the color of the ink. When we added acetic acid with the vinegar, it lowered the pH of the solution and the phenolphthalein turned clear. When you add extra sodium hydroxide, it increases the pH of the solution and the phenolphthalein turns pink again, revealing the ink and the writing within. To avoid the ink disappearing right after I start writing on the page, I made a solution of just the phenolphthalein in the base so that it would remain purple and at a high pH when I wrote on the page. Now you're probably wondering, how does an indicator work? Most indicators are weak organic acids or bases, and they have distinct colors of their different ions involved in the reaction. For example, with a monoprotic acid, the HX is a distinct color, but then the X- ion is also its own distinct color. In phenolphthalein, the XH is clear as an acid, but then after adding base, the X- ion is pink. According to the chemical reaction on the sheet, when you add acid and you lower the pH, it turns the color of the conjugated acid, or the HX. When you add a base, it raises the pH, and therefore the solution turns the color of the X- ion, which is also pink, for the phenolphthalein. Overall, when the concentration of the acid is greater than the concentration of the base, the acid solution turns into a clear color. But when the HX has a lower concentration than the X- base of the solution, it turns pink. These are drawings of the different molecules involved with the phenolphthalein indicator solution. When the phenolphthalein is the XH, or the colorless acid, it has the attached hydrogen and is shown on the left. But when it's the pink base, it looks like the molecule on the right and doesn't have an attached hydrogen, and therefore resembles from the page before the X- ion. So when you add base, you are adding the diagram on the right, but then when you add acid, you are turning the color of the molecule on the left. Basically, when the phenolphthalein molecule loses a hydrogen, one of the benzene rings opens up and the electrons are able to move more freely in the molecules. This less confinement of the electrons leads to the pink, or the closer to the red shade, with lower energy. But when there is confinement with the pi bond, it is an ultraviolet color, which to our eyes shows up as the clear, like with the added acid. This is because the more confined molecule, as seen on the left on the top of the page, has more energy and there shows up as a color with more energy, which could be purple, but even more energy than that is ultraviolet, which to our eyes appears as clear, like when we added the acid to the solution. Here are the sources that I used for this demonstration. Thank you very much for watching and listening.